Hello and welcome to this module on transformer. Navigation tour. Sound control. You can use this to adjust the volume settings for this module. By the end of this module, you will be able to define transformer and its working principle, explain construction of transformers, draw phasor diagrams of working of transformer, make an equivalent circuit of transformer, list different types of transformer as per applications, execute tests and maintenance of transformer, and protect transformer from different faults. We have heard the word transformer a lot in daily lives, but what it is? Transformer is a static AC device used to change high voltage low current AC into low voltage high current AC and vice versa without changing the frequency. In brief, it transfers electric power from one circuit to another. It does so without a change of frequency. It accomplishes this by electromagnetic induction, where the two electric circuits are in mutual inductive influence of each other. The operation of transformer is based on the principle of mutual induction, according to which an EMF is induced in a coil when current in the neighboring coil changes. In this section of the module, we will understand the construction of transformer. From the core construction perspective, transformer is of two types, that is, shell type and core type. Click each to know more. In shell type transformer, windings are wrapped around the center leg of a laminated core. Here, the representation of shell type transformer is given. Here, the construction of shell type transformer is shown. In core type transformer, windings are wrapped around two sides of a laminated square core. Here, the representation of core type transformer is given. Here, the construction of core type transformer is shown. For better understanding of construction, click each of the following concepts and know more. High voltage conductors have smaller cross-section than the low voltage coils. Here is the sectional view of shell type transformer. And this is the sectional view of core type transformer. Here is the construction of shell type transformer using stampings. Here is the construction of core type transformer using stampings. Click each image to know more. The HV and LV windings are split into number of sections, where HV winding lies between two LV windings. In sandwich coils, leakage can be controlled. This image shows the coil and laminations of core type transformer. And here are the various types of cores. We take round-shaped core to have minimum winding copper wire. Let us look at the cut section of transformer to understand it more clearly.
Click each number to know more.
Frame or tank. It protects the transformer core and coils and provides mechanical support to all accessories. Core. It provides the magnetic path for the magnetic flux. Windings. These provide the path for electric current. Core. It provides the magnetic path for the magnetic flux. Radiators. It is used to improve the cooling efficiency of transformer. Drain cock. It is used to collect and drain the transformer oil. Rollers. These are used for transportation of transformer. High voltage bushing. It provides support for high voltage terminal with proper insulation. Low voltage bushing. It provides support for low voltage terminal with proper insulation. Conservator. It provides space for the wire. Low voltage bushing. High voltage bushing. Low voltage bushing. It provides support for low voltage terminal with conservator. It provides space for the wire during change in temperature. Explosion vent. It is an emergency safety device to protect from high pressure inside the transformer.
Transformer oil. It is stable at high temperatures and has excellent electrical insulating properties.
Buchholz relay. It is a gas-operated relay which gives alarm during overload and trips in case of severe fault inside transformer. Temperature gauge. These are of two types, OTI, that is, oil temperature indicator, and WTI, that is, winding temperature indicator. Breather. It inhales dust and moisture-free air inside the transformer. Let's understand the working of transformer with conservator and breather. Conservator allows extra space for transformer oil to contract and expand due to heat produced because of loading of transformer. While inhaling, breather allows dry air to go inside the transformer, and during exhaling, the air inside the transformer is released in the atmosphere through it. Breather consists of oil pot and silica gel. Oil pot catches dust of air that goes inside during inhaling, and silica gel absorbs moisture of the air. Color of dry silica gel is blue, and after absorbing the moisture, the color of the silica gel becomes pink. Now, let's look at the working of a transformer. 1. When current in the primary coil changes, being alternating in nature, a changing magnetic field is produced in the core. 2. This changing magnetic field gets associated with the secondary winding through the soft iron core. 3. Hence magnetic flux linked with the secondary coil changes. 4. Which induces EMF in the secondary winding. Depending on the electrical network where the transformer is installed, there are two transformer types: three-phase transformers and single-phase transformers. Let us learn about single-phase transformer. The AC voltage source injects the AC current through the transformer primary winding. The AC current generates the alternating electromagnetic field. The alternating magnetic field gives rise to alternating flux in the iron core of the transformer, thus inducing voltage in the primary as well as secondary windings. Thus, the voltage is induced in the secondary winding with same frequency as voltage of the primary side. The induced voltage value is determined by Faraday's law. ERMS equals to 4.44 into F into N into phi max, where F is frequency hertz, N is number of winding turns, phi is magnetic flux WB. The single-phase transformers can operate as step-up transformer or step-down transformers. In this section of this module, we will learn about the ideal transformers. An ideal transformer is an imaginary transformer which does not have any loss in it.
For better understanding, we have divided it in two following parts: terminologies, circuit and phasor diagrams. Click each to learn more.
In an ideal transformer, the leakage flux is considered nil. That means 100% flux passes through the core and links with both the primary and secondary windings of transformer. Although every winding is desired to be purely inductive, but it has some resistance in it which causes voltage drop and I²R loss in it. In such ideal transformer model, the windings are also considered ideal. That means resistance of the winding is zero. Now, if an alternating source voltage V1 is applied in the primary winding of that ideal transformer, there will be a counter self EMF E1 induced in the primary winding, which is purely 180 degrees in phase opposition with supply voltage V1. As the primary winding is purely inductive, that current 90 degrees lags from the supply voltage. This current is called magnetizing current of transformer I mu. This alternating current produces an alternating magnetic flux phi, which is proportional to that current and hence in phase with it. As this flux is also linked with secondary winding through the core of transformer, there will be another EMF E2 induced in the secondary winding. This is mutually induced EMF. As the secondary is placed on the same core where the primary winding is placed, the EMF induced in the secondary winding of transformer E2 is in the phase with primary EMF E1 and in the phase opposition with source voltage V1. Here are few terms that we need to understand first. Zero leakage flux. Fluxes produced by the primary and secondary currents are confined within the core. The windings have no resistance, that is, induced voltage equal applied voltages. The core has infinite permeability. It means the following two conditions. Reluctance of the core is zero. Negligible current is required to establish magnetic flux. Lossless magnetic core, that is, no hysteresis or eddy currents.
Do you know the EMF equation of transformer? Click to view the equation. Here is the EMF equation of transformer. E equals to 4.44 BAFN, where E is induced EMF in volts, B is flux density in WB by M square, A is cross-sectional area of core in M square, F is frequency in Hertz, and N is number of turns. In this section of this module, we will understand transformer in different conditions with help of circuit and phasor diagrams.
Drag and drop each voltage bushing on transformer.
Click each to know more.
A transformer is said to be on no load when its secondary side winding is open circuited. When an AC sinusoidal supply is connected to the primary winding of a transformer, a small current I/O will flow through the primary coil winding due to the presence of the primary supply voltage. With the secondary side open, that is, when no load is connected to the secondary side, a back EMF along with the primary winding resistance acts to limit the flow of this primary current. Obviously, this no-load primary current I/O must be sufficient to maintain enough magnetic field to produce the required back EMF. This no-load primary current is made up of the following two components. An in-phase current, IE, which supplies the core losses. A small current, I mu, at 90 degrees to the voltage which sets up the magnetic flux. Here, the figure shows the phasor diagram of a transformer on load by assuming 1. No voltage drop in the winding, 2. Equal number of primary and secondary turns. As shown, direction of induced EMF is opposite to applied voltage. But direction of induced EMF in primary and secondary will be same.
And the primary current is divided into two components as shown.
When an electrical load is connected to the secondary winding of a transformer, the transformer loading is therefore greater than zero. A current flows in the secondary winding and out to the load. This secondary current is due to the induced secondary voltage set up by the magnetic flux created in the core from the primary current. The secondary current IS, which is determined by the characteristics of the load, creates a self-induced secondary magnetic field phi S in the transformer core, which flows in the exact opposite direction in the main primary field phi P. These two magnetic fields oppose each other, resulting in a combined magnetic field of less magnetic strength than the single field produced by the primary winding alone when the secondary circuit was open circuited. This combined magnetic field reduces the back EMF of the primary winding, causing the primary current IP to increase slightly. The primary current continues to increase until the core's magnetic field is back at its original strength, and for a transformer to operate correctly, a balanced condition must always exist between the primary and secondary magnetic fields. This results in the power to be balanced and the same on both the primary and secondary sides.